Hey everyone, my name is Kelly, and I'm a hardware engineer, and I'm also founder and Kura AR, Kura Technology. So we're building AR glass, and I start by building hardware, start by building 3D Tesla coil using like a pipeline when I was at Berkeley. Um, so so I really like building electronics, especially something related to applied physics R&Ds. And so some project I've made in the past, including self-driving robot suitcase, which is there, and DIY structured light cameras, because I was all structured light camera was too expensive to buy. And I was making a filter together with John McMaster, who was there. And so right now I'm making a linear particle accelerator right now, actually in my garage. Next hack session this Sunday. So some unfinished projects like Raman spectrometers. In the past, working on like and dislike motion classifier on your brainwaves. And so I actually, in my college, in my first year, I start as a business major in accounting and finance. So I changed my major 4 times, all the way up to math, computer science, computer science, electrical engineer. So I really valuable the chance I can build stuff. So since today I'll be talking with AR, so I'm talking how I got started. So more than 3 years ago, me and a bunch of friends, we started some group called the Cognitive Technology Group at UC Berkeley. So I was working on, like, before that I was doing machine learning stuff. And I was really interested in brainwave because I feel like all of those classifiers can know people's emotion without talking, without click. So, and I was designing dry pad-based active EEG sensors, and also making that with some Atmel microcontrollers and ADCs, which is like this board, and designing capacitor-based sensor, which is the gel. And I was also working on machine learning to do like and dislike classifier. Like I watched 30 videos, which I don't know what I'm watching before I watch those, to record my brainwave and label it as like and dislike, or that I don't care. And then I writing the algorithm using time series to turn time series into frequency domain, and extract features, and to using those to predict for the 20% of the new videos, to see if I like it or not using existing trait classifiers. And I was at a point I almost turned that into a startup. Then I realized like no one is going to use gel on their hairs if the sensor is not good enough. And no one want to wear those sensors without real-time feedback. And people want to wear this everywhere, not just the headsets. They don't want to look like their phones. They want a real-time interface, so they can know where they are, can see what they see. So the solution will be a wearable computer, which is AR glass. And this is like more than 3 years ago. And at that time, like I was very new to optics and even a lot of electronic stuff. But I searched for all the AR glass which is on the market or not launched yet. So I realized the biggest problem is optics. Like that time, like Epson Memorial, it having 23 degree field of view, and it's like Manta, like the Manta 1, which is almost more than $1,000, and it's not on the market yet. So I set my goal to build my first AR glass as both a learning experience and turn this into a small product. So talking about AR optics, like because AR glass you need to see, if you can't really see clear, what can you do with it? So for the major type of AR optics is including like waveguide, diffraction waveguide, reflection waveguide. So diffraction waveguide including like HoloLens, Magic Leap, Vuzix. Actually, all of them are from the original Nokia patent. So so those two, Magic Leap and HoloLens design, was actually very similar to each other. And reflection waveguide like Lumas, and freeform prisms like this one is more simpler design, and it's always normally working with a micro display, sometimes with LCD as well. And including Google Glass, Net Plus with a Chinese company, the Intel Vant. So they're using VCSEL as a laser light source, you're doing monochromatic. But all of those are small field of view, 10 degree field of view, 20 degree field of view. For showing like notifications, but not for animation. And also there's larger semi-reflection, semi-reflectors. Actually, the freeform prisma and the larger semi-transparent reflector is actually the geometry is nothing different. The only difference is they're using large LCD or they're using micro display. So Manta, Mira, those glasses working with cell phones, for more, those more mature to launch. There is more in R&D phase, including variable focus, which they're using liquid lenses. Professor Gordon and Stanford, they're using liquid lenses by eye tracking to control the focal distance for these lenses, according to where you're looking at, how far you focus. And there is also multiple focus. There was a difference between those. Variable focus is actually changing that, but it always focuses on one surface. But multi-focus, it means it having multiple focal depths at once. For example, the new Magic Leap 1 patent shows that they have 2 different focal plane. And Avegant new AR demos is Avegant is mostly using 4 different depths of light source. So they do the engineering into light source to make phase delay or something like that to make you feel the light source at different positions. But Magic Leap is they doing that through the waveguide. And also there's foveate display, including like a company just raised a lot of money, Virgil. Most of those coming with eye tracking, so did Virgil. And also P-mirror displays, which is similar method using semi-reflectors, but they put that in a very, very small mirrors. Small P-mirrors which have a curvature, but they put multiple of those P-mirrors on the surface of your glass. So each of those pins covers a small amount of field of view. So together, they cover the full field of view. And the problem for this is the field of view is very small. And although you normally cannot see those dots, but when you actually focus near those dots, you feel this stink on your lenses. And what I'm holding here is it's actually a diffraction waveguide, which we got from a European company called True Life. This one thing is costing they sell for $1,500, and this is this is a micro lens array which can be used to make light field imaging and light field display. So let's first talk a little bit background about how waveguide works. And first is diffraction waveguide. Diffraction waveguide, which means they're using sub-wavelengths wide features. So diffraction is like interference with wavelengths. To do the interference with wavelengths, like people, like we all remember the double slide experiment. Basically, you treat the light not as ring, not as line, but you treat those as waves. So to interference with waves, you need to have features which is repeating in a way which every single feature is smaller than one single wavelength, which is smaller than 400 nanometers. And for example, like this surface, this is actually from Magic Leap's new released patent from a month ago. And this stack 6 of those, and it's 3 meter depth, and there is farther depths. So the new Magic Leap glass having 2 depths from what this pattern illustrated. And so because those interference is very specific to one different wavelength, so for RGB you actually need 3 different type of features. Those are for green, those are for blue, and those are for red. So the good thing about this is it can be very small because the feature is very small and it's not curved. Normally it's not curved. And the bad thing about this is very hard to manufacture because you're putting like tens of thousands, hundreds of thousands of those features on one small surface. Couple defect on those is very hard to detect, and those will cause ghost image. And because you predict the light as wave, not as ring, so you actually can't predict a large amount of where light goes. So that's caused a lot of ghosting image. So it's very expensive, and right now this method is not mature enough for mass consumer use case. So then reflection waveguide. So Lumas is using reflection waveguide. I actually like this method but better for now. So look at this, they're using, so this is all the same. They're using different lighters. The light goes from here, hitting the surface. Some reflect out from here, some reflect from here, some reflect from here. So basically, they cut a curved mirror into a small stage. Each of those reflect out a portion of the image you would able to see. And you also don't want some image which shows on this surface double to be shows on this surface again. That's why people doing engineering work for the light source to make sure it hitting it at the angle which will be, once it hitting this surface, it can pass through more than the critical angle, so it can go to the second one, go to the third one. And if there's any double image, they want to make sure it falls into the range which people's eye cannot really see, like maybe here. So this method is right now it's more clear. It's less ghosting image because there's no nano structure on this. But to actually align those at the critical angle, because this is like multiple moving parts, you need to actually glue those. You stack those, align those, glue those, and cut those. Like cut those like this. So it's, the yield ratio for this is actually pretty low right now. So like one piece of Lumas waveguide right now, 45 degree, or the 40 degree actually costs $1,500. So and you can actually make your own. So I was in last 1 year I was exploring how can I make my own diffraction waveguide. I got a membership and staff in Stanford nano fabrication facilities. So there they have plasma etching machines. They have small structure laser etching machines. They have electron beam sputtering coating machines. By paying those, if you're students, if you prove you are students, you can pay for $100 per hour. It's really worth. So, and so everyone in benefit there, and you get access to all of the newest nano fabrications. And there's also every Thursday there is office hour there, which is people who have been very experienced on this for 20 years will teach you how to make those. So actually, like it looks very new for head-mount display, but all those manufacturing method is already quite mature in the nano fabrications industry. So like I had a friend who making like blood testing machine there, and I was using the sputtering machine there, and so let's talk more about reflectors and freeforms. So there's two types of reflector freeforms: on-axis and off-axis. So on-axis including ODG, Google Glass, which is easier to design, less distortion. On-axis, which means it. So this is off-axis. You see, so the light source is not on one single axis. That one is like, although it goes down, goes there, it's always in the center axis. This one is tilt here and then tilt there. It's for off-axis, most people using ellipsoid. For on-axis, like spherical or parabolic will mostly works okay. So off-axis, you don't need one more surface there to do the right angle of signal reflections. It's simpler to do the design, and but there's more distortion you need to deal with in the software side. So and it's also comparable larger field of view, and more transparent, because you don't have to have that one to there to decrease the transparency by half again. So this design is actually from the Intel Vant. So this. Also back to almost 2.5 years ago, I set my goal to make my first large field of view AR glass. It's like, I said how much field of view I want. I look at the human field of view as like 110 will probably be fine. And this is actually the result I made. So the goal for this was initially not to turn us into any product or something. To like eventually first I want to learn how to make AR glass, how all the criteria I had to hit. And I had never thought this design would something I would be sold or I would be sell. So I just tried to learn initially. And how do you make a more than 90-degree field of view AR glass at home with accessible tools? So me and a bunch of friends, we try a lot of different methods. And one way to do that is actually, you can use some CAD softwares like Autodesk Inventors or SolidWorks. You can generate equation generated surface, which you can put different different parameters, six parameters, 8 parameters, generate equations to do like hyperbolic, parabolic, ellipsoid, or even more complex equation generate. So those turns that into a 3D surface. And you can put variables, constants there by changing the surface. So you can iterate generating those surface by a mathematical equation there. And after we did that, we also wrote our, me and another graphic engineer, we also wrote our OpenGL, C++, and Python script to generate those surfaces with more freedom than the CAD modeling softwares, and turn us into STM files. Either works, and the first one is simpler. And this is some of the surface we generated, and this is in Blender. And so, of course, we need to do testing, not only doing. So, how do we test and redesign without actually manufacture it? So, and there's a really good open source software called Blender, and you can import your geometry into that, and you can put a checkerboard up to the top. And then you can put a camera and your pupil positions. The camera looks towards the reflector surface, and it sees the reflection of checkerboard or any image. And you can kind of simulate where a human eye would be able to see how large the distortion is, like how far the image focuses. And this is one of the results I put. I was putting a sample screen there. And then by doing that, you go back to adjust the model in Autodesk Inventors or other softwares you're using. So this is the software we wrote using OpenGL, C++, actually using DirectX. So it's modified from existing software, and was able to do 3 functions. One is to draw a bunch of rings, and another one is doing pixel-to-pixel matching rendering from the image, from the display to the image plane. And then is to able to adjust the viewing point to move stuff up and down, left and right. So Keyshot would also works. It's something similar to Keyshot is similar to Blender. It's another which actually a little bit better, but it's not open source or free. So finally, so after we test the redesign again, once we are satisfied with the results, so we actually want to see that. How do we manufacture that? I don't have any funding like 2.5 years ago. How do I manufacture that with a very small amount of money? So basically there's 3 steps. So first is a CNC machine the mold for the lens. Second is vacuum form on top of that with a transparent material. The third is coating that with semi-reflective metallic layers, so you'll see the image, not lose all the image, because you need to having reflective ratios able to see what you're having on the display. So CNC sounds easy, but it's not that easy. Initially, try to save money. I take CNC machining class and tech shop. So using the Tormark, first to turn my stem files into G code, and design the rough cut, the fine cut. Rough cut which means the quick cut, which every stem is very big, but it's not accurate. It's not very accurate, not very fine, because this needs a smooth surface. So you actually, after the rough cut, you need a very fine cut. You need to actually changing to a very small ball tip, which is using to make smooth surface. Sometimes if you're having a good fine cut, you actually don't have to polish in those. So, and planning the paths to where to cut from, where to end. And so I'm doing that so I work on those with a more experienced CNC machinist. So he go over what I should take care of during the steps. And after making those, you need to polish those with polishing compound, sandpapers, cotton spinners, bunch of stuff. So I actually spent the whole week. Almost I live in tech shop for like, at that time tech shop open 24 hours. So And I literally during the time the liquid cooler for those machines are broken. I stand next to those machines, hand spray the liquid for 7 hours from 10 p.m. to to the morning. So I do it for 3 nights or more during there, and I finish the first mold, and I polish those, and it's fun. It's a lot of work, and I decided not to do it again. So, and because the time you spend compared to the money you could spend on sending it out for someone to CNC machining those, I contact more than 20 CNC machine shop around Bay Area. This is one of the most hurdles I found. They make parts for Tesla, they make parts for SpaceX. So they can, most of those, if you're okay with 1 vector or 2 vector, they can make those with each of those with like $200 to $300 count and finished, polished. And the one you see down there was actually one I made from China. So they actually ship it back from Shenzhen. The shipping cost is more expensive than to make those. So those are made from stainless steel. They recommend using stainless steel because they say it's easier to polish. So after we make the mold, and we need to vacuum forming the lens. So at that time, so I take the vacuum forming class and tech shop, and then I do the vacuum forming. So basically something like this, I using a similar method, and I realized without good temperature control, there's going to be a lot of air bubbles. It's going to be a lot of gaps. So then I found a bunch of vacuum machine shops, vacuum forming shops in the Bay Areas. I just sent a job to one of them. Cost me about $500 to make a couple pieces of those. And so after I got those lenses cut it out, the process is to coating those. So basically their coding is to using high voltage magnetic field or high temperature to get a sample, metallic sample. The particle will be bombarded by the electrons in this high electrical field, strong electromagnetic field. So for example, aluminum or gold, those particles will actually get off from the metal block. If you put the surface in the middle, they will hit the surface, then they will stay on the surface, and later on when it's cooled down, you'll see a thin film on that. So so I try to do 70% reflectiveness. I do some basic calculation to see how much was thickness of aluminum I need, and so how much time it will need to stay in the specific machines, and testing the machines. Basically, the first those calculations end up not working for me because I have no idea until how each machine actually works. So the one you see up there was actually I was taking a nano fabrication class at Foothill College at that time. So I told the teacher, so I have this problem. He told me his dad was actually the inventor of sputtering machine. So okay, I'm good. So I go to his dad, and his dad's still having one of the machine he built a long time ago in his garage. So I go to there, he helped me on doing the coding. But the problem with sputtering machine was actually being used for coding scanning electron microscope samples. It's very small, but my lens was 3-inch diameters or around that, and I need uniform coding. So basically, you get if you not code it enough, it's the peripheral area is all with not enough coding. If you code it too much, it can actually melt. The center area is much more fried than the peripheral area. So as well as another problem I found is PETG is very, very hard to code because it's having a low melting temperature, and it can have an ionized effect if you put it in a chamber which having electromagnetic radiations. So PETG will actually out-drip inside those. But because PETG is very easy to vacuum form material, all my vacuum forming shop recommend me to use those to save money, but they actually failed in all the coding process. So using acrylic or polycarbonate. So I eventually sent it out for sputtering coding by a friend which was introduced by the inventor of sputtering machine. He actually got the job done with just $200 at that time. I told them I have no money. So finally, the result of those was those lenses, and and this is the one which my co-founder built at the same time. So let me see. Finally, we got those lenses. So then we got those lenses. What other fun stuff we could do? I was talking with a bunch of friends during that time. A lot of people from Hex. So it's like there is in Japan or China or somewhere, it's like in hotel room there is those transparency changing films on the wall. You can actually switch in the transparency from transparent to non-transparent. It's called liquid crystal light valve or PDLC film. So how about we can do a AR VR variable transparency on this? So I go on Alibaba searching for the cheapest PDLC film I can buy. It's mostly running on 15 volts AC or close to that, and you plug into a power plug. So, but my goal was running it on battery portables. So I built a small boost converter for those, and later on I found this very special film which using liquid. Actually, so most of PDLC is says liquid crystal. It's not actually liquid, it's dry particles. So its conductivity is very low, so they need high voltage. So it's actually one type I found, which is actually in the bottom here. So they actually using its liquid type liquid crystal inside, so it runs on 9 volts. Oops, those are videos. So I guess, not sure if those can be wrong. It's fine, but you will just see those changing transparency immediately. And so this is black, another one is white. So you can actually, I talk with liquid crystal physicists, they told me you can actually put dye into those. So you can make those fully black out. So electronics part, so we make the optics, we need to put displays out there. So I took apart my oculars, I bought a Vive, took apart, and start sourcing out because OLED is having low brightness. So although it's a high contrast ratio, but the brightness is not as high as LCD panels. I bought some LCD panels from Alibaba, from Shenzhen, like a bunch of Shenzhen company like Sharp, or their spin out makes those. So I initially using one single panel as I switched to 2 panels. There's a reason to using 2 panels, because if you put an angle between those 2, you can actually increase the field of view for a little bit more. After we got panels, electronics is also leap motion for gesture tracking and the front. So we 3D printed the case. So we eventually bought a form lamp. It's very good for very fine features, but the form lamp resin is not so good for structure, which needs screws for holding a strong weight. So I was also using U-print to making those. Stratasys U-print, and you can print multiple parts at once, but need 2 hours to dissolving the supporting material in hydrogen peroxide tanks. So tried a lot of different printers, some even more like MakerBot, similar to MakerBot. So those 2 are, if you would need industrial design using form lamp, if you need quick prototype, Stratasys U-print is really good. So this is our kite model. So and all parts. So it's not. So all parts in the headset eventually it including 3D tracking cameras, 1st generation, 2nd generation. This camera is open source right now, and so we're using Zotac computers. Like right now we try to move into the Qualcomm Snapdragon 835 board, which is mobile CPU, and this is the device. On the front you see the transparency changing films, and the leap motion for gesture tracking, and the camera, the stereo RGB camera for SLAM position tracking. So we actually modify an existing SLAM algorithm to be more suitable for AR use case. So here what we got is, this is actually a link to Twitter. This should be a demo for what shows on the glass. Oops. I'll show it after. I'll show a demo video after finish all of this. So basically, we got a large field of view AR glass. It can working with a cell phone because you can put your phone there. It can also working with a similar size of LCD. It changing transparency. It having inside out tracking, but it's too big. because in this way, with just one simple reflector, if you want large field of view, you need to use a very large display panels. How do we make it smaller and still keep a large field of view and easy to manufacture? So this is my first optical design, and we move on to our second. So some fun stuff we found. So this was actually optical fiber taper, because with some lenses, optical fiber taper, which means small lenses, which is millions of small optical fiber arrays inside those. And those transfer the image directly from one end of the optical fiber to the other end, and it's very dense. And so this was so this can function as a magnified lens, because lens will break down the RGB light, because it's a block, so they can transfer wherever they want. But with fibers, light can only transfer within one fiber. So the chromatic aberration will be limited to a diameter of one fiber, which is really good. So I actually got a lot of those optical fiber tapers at that time. So the first one's looking under a normal microscope. The second one's looking under a scanning electron microscope. So we're actually able to convince Corning to let me using their scanning electron microscope during that time. So then we started on version 2. Let's put more complexity into optical design. So we get using some new tools, and because first one we're using LCD and OLED. And so it's very dim, it's very big. So this one, do a quick search for like different type of display. Alcals, which have been using a lot of projectors, tends to be the best, because you can design your own light source. So the light source goes, the reflective alcals, light source goes here, goes through a polarized beam splitters, changing then hitting the surface, changing the polarizations. And is this control here, every single pixel, the liquid crystal, it twisting, and once it matching the polarization on the top of this this panel, the light can pass through. If it doesn't match, it cannot pass through, changing the brightness. So because light source is not in the back of silicon or glass, it's right there. So you can actually designing light source driving, so to turn the brightness to be very high. So this is developer kit which I got. It's open source. The board is mostly open source design. So then it's get cooked and educated in real optical design. So there's two type of head mount display optical design: pupil forming design and non-pupil forming design. So pupil forming design, which means you have a pupil plane as one single plane. All the light goes from image, focus, and then one single plane. That's your eye relief. But non-pupil forming design, which means all light pass through one hole, pass one stop. You put a stop here. But that one is more efficiency. So if you put your eye here, you're supposed to see majority of all the chiffering. Is here is some is in focus, some is not in focus. You'll see partial of the ring. But the good thing about this is most head-mount display actually using non-pupil forming design. The reason is because this way you have a much larger eye box. That one, if you put your eye a little bit farther or behind that plane, you cannot really see the image. It's mostly being using a telescope or microscope design. So we are using the second way. So there's optical design software called CodeV, which probably all the optical major master students or undergrad using those. So this is actually a practice. So of a practice AR optical design, which I did follow up the instruction from CodeV. So you can optimize for MTF numbers. You can put different shape to the geometry. You can put like Zernix surface. You can then, if you click that surface in there, you can change the parameters, and you can set your goal for optimizations. And this is the 2D view. So I started learning these softwares. And it's very expensive. I found some way to get a free dongle from a friend of mine initially, and so in this software you can design the equation for every single surface of the lens, and you can change the space between every single lens surface. You can set optimization functions, analysis for MTF numbers, which is one of the most useful parameters in this. Spot size, which means if you trace a ring, if it's supposed to focus on your image plane, what's the spot size it focus. If it's very small, it's really good because it means it's very focused. If it's a large circle, which means it's not that focused. Chromatic aberrations, which means the RGB breakdown because due to the shape of the lens. Ghost image, which means if you have two surfaces, you hope the light all bouncing back from the first surface, but actually the light goes through the first surface, go to the second surface, so you'll see. Manufacturer tolerance, which means how much error you can make in the assembly and the manufacture for it to still work as your expectations. Field of views and the diffraction. So we are using code wave for our second design. This is actually exactly from our second design. So MTF number optimization chart. So you always try to hit a goal, and 20 is higher than 0.6, and 50 is higher than 0.5. You can see 3D view, and this is where light all got focused to. So we spend like a lot of time, like 3 months, on trying to optimize this one single design. Like me and a couple of optical engineering working on this. Like I was learning everything from scratch, like an idiot, to ask people questions all the time. So so this is what we learned from doing the design with Code V, which is a good head-mount display design. The eye box need to be bigger than 1 centimeters, because otherwise, if your height people have different eye size, different IPDs, different head size, different nose size. So if we're on different head, you cannot really see the image if the eye box is too small. So the spot size, which means the focal, like the focus spot, you want your spot size to be less than 1 single pixel size on your panels, because that means if you're tracing the light from your profile back to your panel, you can still every single pixel is clear. MTF numbers, which means MTF actually means if you this slice, which means line pairs. How dense those line pairs get, you can still see it as line by line, not green. It's like if people wear a strip shirt, if they stand very far away, you'll see them as not as strip, but as green color, like green color. So strip MTF number, which means the contrast ratio clearness of the image. So you want the MTF number is like to be, this is from our experiment and some standard. So you want to optimize for low distortion, low chromatic distortions, low ghost image, low street light, because street light which means the light bounce back and forth on some surface on the edge of the lens in the light tube. On some surface you don't want to, and there is a process to optimize for that. And also, for sure, to analyzing the manufacture tolerance to make sure it's manufacturable. For example, our system having the 50 micron manufacture tolerance from end to end. So this is very tight for CNC, which is okay which is not possible for vacuum forming. This is good for diamond turning or injection mode. If so, some NASA telescope need like 10 to 20 microns. Like you need to find this number out, because this would define this method you use for manufacture. So we use mouse crystal glass-based materials because it's easy to polish. The clearness is better than plastic normally, and you have more choice in the first version. But it's also really heavy. So for coding, we're using electron beam coding for this. And because electron beam, you have a dome instead of like very small chamber for sputtering coding. Electron beam coding, you normally have a very large chamber, has a dome shape. So it's coding like more than 5 lines at once. And we make a really shitty decision for when we making this. It's like this, everything was like make right. Only the holding for this is shitty 3D print. And this whole thing basically destroys the overall tolerance for this. No matter how accurate your lens is, if you put in a 3D resonance-based 3D print cases which having 2 millimeter tolerance instead of micron level, like everything just going to distort. You can't really trace back where the error coming from. But to save money and time during that time, I just really want to see the result. So we use that way initially. And electronics, of course, you need electronics to drive your display. You need two LED drivers. So we made a custom made circuit board for driving the LCOS and LEDs. We use a lattice FPGA, like you see on this board. So this taking the HDMI input. This one converts the HDMI digital into analog and traces it to this board. This board having a custom ASIC, which is made by display companies, and having LED drivers using PWM to driving the LEDs and display, which is synchronized. And we're debugging that through I2C using Biggerball Blue, so we can actually do it through the internet. So it's better using SPI because it's faster. So this is our electronics workbench, and this crazy octopus hand to holding stuff. So we make some stupid mistake when we're making those lens mold. So it's the shape looks exactly like symmetric circle, a globe, but it's not. It's not symmetric in horizontal or vertical way. But I forgot to put a hinge on this mold. And they make this and ship it to me. I realize, okay, I can never find direction. So I try a lot of ways to find direction, even by starting building Michelson spectrometers. So to see if Michelson spectrometer, if it focuses, you'll see a concentric circle. If it doesn't, you'll see line by line. So I actually got all the parts to building that, almost building that. And then I just decided, okay, let's just make this roughly working, and then let's move on to version 3. So it's made in Shenzhen, 10% off the local price. The factory owners doesn't speak one word English, and using QQ, and it's shipping back to here. It's actually not that bad for the price, but just like we should make it square. So version 3 currently is I'm making the version 3 right now. Is to you see the version 2, the optics is still very big. So basically we prove the large field of view will be working. The large field of view could be done through micro display. The version 1, I'm also just trying to teach myself everything. The version 2, I'm trying to prove you can do a large field of view, low distortion with a micro display, which is like 11 millimeter diameter instead of using a large panel LCD. We cannot prove that. And version 3 right now is shrinking the size, optimized for all the parameters, actually using the right way to manufacture this. To have better optical qualities, we upgraded from 720p per eye to 1080p per eye, and we'll be running on a mobile CPU, which we are currently hacking around with Qualcomm or Rockchip. Rockchip is a Chinese Qualcomm, and they both have very bad Linux support, and only thing runs on both is almost just Android. And so, besides AR, I like building side projects when I have free time, which is barely have free time. And so this is in my garage. So I'm running a hardware hacker community in around San Francisco in our house. So we have like monthly hack sessions to actually building stuff. Some ongoing project including a particle accelerator, Raman spectrometers, mini Tesla coils, and this Facebook page, if anyone interested. The upcoming hack session is actually this Sunday, 5 to 9. We'll be working on the ion source for the particle accelerator or the mini Tesla coil. So this is a corner of our office. We have a lot of hardware here, which is too high. I have to have a ladder there to able to catch the top. So we was planning to bring an AR demo there, but I was so rushed when I came. So if anyone want to try our AR demos, feel free to stop by our hack sessions or visiting our labs. So it's contact information. So and last, I want to actually show what we get showing on the glass. It's actually on my Twitter. This is a demo directly shooted on the giant reflector. So the one we're using LCD and the vacuum form CNC machine the mode. This is we make a distortion correction algorithm. This is a camera we're directly shooting through that. It's a small dragon you can see flowing in the air. So if you want to come to try our demo sometimes, you'll see something a little bit better than this right now. Oops. Yeah, more questions? So right now the plan is for the first version so for the second version, no, for the first version we make, for the reflector one, I'm open sourcing that whole thing. And for the second one, which using micro display, will be turned that into optical module product. And there's a lot of more work we need to do with that one to optimize the size and the optical quality.